anyway you're here and joined. We're pretty excited to have you, and especially today you are closing our event. You're the last speaker for today, so pretty excited. How are you?
Yeah, I'm doing well. I was honestly hoping that I could make it to Ukraine, but it turns out that I have to do it online, unfortunately. Maybe in next year I will be able to visit you guys because I'd love to, but yeah, given the situation, it's a bit hard. But it's doing great. The weather is a bit unfortunate, but I'm looking forward. I saw some very nice talks already, some nice discussions. So that's
Thank you. I saw in the call for paper you mentioned that would like to have a tour in at Lviv. So
yes, exactly.
Let's plan it for next time. Definitely, yeah. Looking forward then for next time. And why I mentioned that it's a pretty excitement topic because this type of testing not commonly discussed, at least in my bubble of engineering. It will be something different, like unit testing, maybe integration testing, something, etc. So that's why it would be pretty interesting to hear some insights from your side, and pretty curious to hear what is special in that type of testing. Yeah, and why do you selected that area to talk?
Yeah, so just like you, at some point I learned about it. In my case, I was doing my master thesis on test effectiveness, and then I found this tool, and I noticed that there's very few people that know about it, even though it's quite an easy to use tool, or at least a good tool to know about. And that's also the goal of this presentation, to give you another tool that you can add to your testing suite or testing toolkit. You don't have to use it, of course. That depends on the situation, which I also discuss at the end of the presentation on when you should or should not consider this. But yeah, like you said, there's a lot of people that don't know about this, that it exists, and I think just awareness already is quite nice. At least you take home something.
Great. Then I don't want to keep you longer. Let's get start, and let's hear about this new type of testing. Yeah.
Okay. You can see my slides, right?
Yeah, all good.
Nice. Okay. Then I can just need to hide this pop-up here. Yes. So indeed, oh, now the presentation is gone. Let me get this back. Yes. Yeah, so I'm going to be talking about mutation testing. My name is Paco van Beckhoven. I've been working for the past 10 plus years in software engineering, which I learned quite a lot of things on the go. I'm currently working in Switzerland at Hexagon's Innovation Hub, where I work on HXDR, which is a cloud-based platform that allows users to view large 3D models, export them, and sort of explore digital replicas of real-world application using various 3D models. Most of this you can already forget, but that's the platform at least I'm working on right now. But the reason I'm here is, like I said, I already have some experience with mutation testing for my thesis on test effectiveness. And I really like code quality, and those two made that I really like to talk about this topic to enlighten others and at least tell about its existence. Now, I want to start off with a small story about quality. So this is a story about my graduation internship, where I was given the task to improve and further develop a traffic-related Android application. And as I started, I did everything according to the textbook. So I refactored the code to increase testability, or from static to dependency injection, measuring code coverage, starting to build integration tests. And with Android, you can do all kinds of cool stuff with checking if notifications appear, if you're simulating a car driving around. Anyway, I wrote at the end a nice graduation report, which was mostly me telling about how I improved the quality this and quality that. But then the problem was that at the very end, I lost a full grade on not actually defining what quality is. So just to make up for past mistakes, I want to start with a definition of software quality. According to IEEE, which is a research publisher, they say the degree to which a system, component, or process meets specified requirements. And you could more well summarize this, or alternative way to say this is how well did you implement the requirements. Now, this is still a bit vague, but luckily there's also a nice ISO 25010 model, which helps us measure, but also structure these requirements mostly. And then while looking at this and looking at what I wrote in my graduation report, when I was talking about software quality, I was actually just talking about maintainability mostly. I spent a lot of time on improving the maintainability, but security-wise, for example, I didn't do anything. So, and the other thing that I like when looking at this table is that you can see that there's many different perspectives of software quality. Perspectives that don't always align. You have the classic between people that want, the more stricter the security gets, the less usable usually these flows get. Even though we might have conflicts within teams, in the end you all have the same overarching goal, which is to improve the overall quality. And in the end, that depends on the requirements. So if there is no requirements on usability and your application needs to be super secure, that means that your application is still fine if it's not very useful because there were no requirements, so you can still say it's good. For now, for this presentation, we're going to be talking about testing mostly. And specifically, we're going to be talking about automated unit tests. So I want to start with, just to get us all aligned, what is a unit test? So for this, we have a very simple example, the calculator class. So this one does multiplication, A times B. Now, if we would add tests for this, unit tests, where you test the smallest possible unit, we could add 2 different unit tests, for example. Well, we could add many, of course, and there's many ways to test the calculator, but for now, you do multiplication, see if the outcome is as expected. And just because it always feels weird, you also check the corner case of not division, multiplication with 0. So this is what we call a unit test. And we write these tests for various reasons. And I think the most important reason is that we write tests to make it easier to make changes to existing code and to sort of gain confidence that whatever we're changing doesn't break anything. So whatever we make a new change here, that not something here suddenly falls apart or when you refactor things. But actually, there's unit tests have many more benefits. One of them that often is forgotten is that tests can also serve as documentation. So when you're trying to figure out what a certain piece of business logic does, the test can actually give you some hints on what is going on, what is going in, and then what you can expect from the outcome. But it's also a nice way to document certain decisions. So in the past, to give you an example, I was working at a company where we were building a warehouse service, and we had an endpoint that returned both deleted and non-deleted warehouses. And it was also deleted warehouses were returned on purpose. However, we only had tests written for warehouses that were not deleted. And then at some point we forgot about this. The next person came in and thought we had a bug, because it's weird. Why would we return deleted warehouses? It was a soft delete, by the way. So he thought we had a bug. We all thought, oh, this is indeed weird. So we changed it. And the funny part is that when he fixed this, none of the tests failed. So he didn't really have to change the test. And that was actually the problem, because as you expect, it was actually intended behavior. So indeed, 5 minutes, maybe a day later, front end came by and say, hey, where did the deleted warehouses go? Whereas one simple unit test where we would have also had deleted warehouses in the test set would have prevented this bug from making it all the way there. So it sort of served as that could have indicated that it was a deliberate decision. Another one is the feedback cycle. So the classic, more explorative approach is that you implement something, and then after starting the entire application, you figure out at the very end that you have a null pointer exception. Whereas this probably could have been easily caught at the beginning if we just written a unit test. And those unit tests we have to write anyway. So if you would have done it at the beginning, you would have saved this whole iteration. Now, one that I like particularly, and this is, of course, a bit of an extreme quote, but especially this one is all for all the consultants out there. Consultants, I was also a consultant for the past 5 years, in which we build nice things. We go to a greenfield project, we build something nice, and then once we get bored of it, we sort of run off to the next assignment, leaving others to deal with whatever we created. And now I had a colleague who always said to me, you always come at this crossroad, right? When you're developing, where you have the choice to either spend more time on tests or documentation, or click the approve button, click merge button, and not have to be bothered with this problem again. And he is still, to this day, the voice in the back of my head that says, okay, think about what it would be if you were in the shoes of the person that's going to maintain your code later on. Think about the next John or Jane Doe and how they would feel about you taking a shortcut here. And that usually is enough to get me back on the right path. And the same goes for testing. That's why we write tests. We write tests because we want to make it easy for the next person to work on this project. And if all these reasons usually are not convincing enough, then usually there is a boss, an architect, or a team lead who's telling you to write unit tests. And at the end of the day, most of us are writing unit tests. So we're all happily adding more and more tests, but we also sort of run into a problem. Because as a project evolve and grow further, the tests also evolve. But the problem is that tests are often missed when refactoring or get a lot less attention. And it's not just during refactoring, it's also, for example, during reviews. Whenever we make a new feature, we spend a lot of time checking the production code, checking if everything makes sense. But then if we start looking at the tests, it's usually, oh, the test passed. You should have probably written good enough tests, so then we sort of accept it. And then if we look at what we do monitoring-wise for test code, there's not a lot. There's a lot of metrics we do. We look a lot in Sonar at the production code, but at the test code, there's effectively actually only one real metric we use, which is code coverage. And with code coverage, we measure the degree to which the source code of a program is executed when a particular test suite runs, the most used metric. And actually, this is quite nice. So I wanted to go over the different coverage metrics and just see how they help us. So if we look at a very basic example. So I have a method, and this is the context of a conference. At the conference, you can submit proposals to do a talk, just like at JavaDay Lviv. And we pass the number of open proposals that we have and the deadline. And now whenever the number of open proposals goes beyond the max, or whenever the deadline is exceeded, we get an error. It's fairly simple. Probably would have written it somewhere else in a different way. But now if we're going to look at code coverage metrics, the first and simplest code coverage metric there is would be method coverage. And with method coverage, it says you just need to write effectively one test calling this method, and then you have 100% coverage. So we're going to add one test in which we say we have no open proposals yet, and the deadline is 100 seconds in the future. Now, 100% coverage. We can take it another step further. If we look at statement coverage, then you see that we missed. It's also often called instruction coverage, and you see that we missed the unhappy flow here. So we need to add another test for the unhappy part. And there you'll see that, so we add another test with 5 open proposals, which is more than the 3 that was allowed. So now we return an error. And we can take this even one step further. There's also some, the next step is condition coverage, or branch coverage also sometimes called. And there we check if each Boolean sub-expression is evaluated to both true and false. So what we didn't test yet was whether our deadline check was actually ever going to return true. So we need to add one more test. As you guessed it, we add one with no proposals, but with a deadline of 100 seconds in the past. And now you see that with code coverage, we actually already have a nice set of tests written here. And the other nice part is that actually it's very easy to measure. So the code coverage is pretty nice. It helps us to find the blind spots of whatever we're working on and write better tests. And also it's really easy and cheap to measure. So what you see, measuring code coverage is just a matter of instrument the bytecode, run all the tests, and then get the report out of the instrumentation, and it's done. It takes no time. However, code coverage can also be quite misleading because it doesn't give you any guarantees of the tests themselves. The only guarantee that code coverage gives is that whatever is covered didn't crash. Because if I take this test, for example, there's no assertions in here, but this test does generate coverage. And this is exactly where we sort of reach a problem that, hey, this code coverage looks nice, but actually maybe we're missing something. And this is where test effectiveness comes in. Test effectiveness, with that we measure how, we're going to start with testing the test, and we measure how well the tests are at detecting bugs. So sometimes you do this yourself. Whenever you have a pull request open, you're reviewing something and you want to make sure that the tests actually make sense. Or when writing tests, typically you also want to see it fail. So you make a change in the production code, You swap some if statement, and then you hope that the tests fail. I mean, doing this by hand is a way to do it, but this doesn't work for regression. And it's also not really consistent. It's not really reproducible, which is where, and there we are, mutation testing comes into place. Mutation testing is a technique in which you simulate bugs in the form of typical programming errors in an automated manner. So we get consistent results, and we can automatically run this process. The first step in mutation testing is generating mutants. And each mutant is a tiny altered version of the production code. There's only one very small change. For example, if you have this method, is allowed to apply for driving license in the Netherlands, where I'm from, it's you have to be 17 years or older. Now, one mutant would be the entire code base stays the same, but just this condition is inverted. And actually, we can, for this method alone, generate more mutants. We can also, besides negating it, we can change the conditional boundary. So rather than larger than or equal to, it now becomes larger than. So it sort of is testing whether we check if the edge cases is tested, or always return true or always return false. And there's different kinds of mutators. There's also anything mathematical. You can invert every plus automatically into a minus, multiplication with division, and vice versa. There's also operators for modulo, the modulo operator. All to make sure that our tests sort of are able to capture these mistakes. And one that I particularly also like is removing void statements, because it's important to know, by the way, that every mutant should result in compilable source code, because we're not testing the compiler, we're testing our source code, our logic, which means that you cannot start removing random lines, but void statements are ones that can easily be removed. So in this case, we want to make sure that actually, if I remove this, would any test be able to pick this up? Now, once we have generated a lot of mutants, we come to the next step of which is the analysis. And then what we do for each test, we will execute the test. So for each mutant, we will execute the tests. And as soon as one test fails, because of this small change, that means that the mutant is killed. And if the mutant is killed, that means that our test did their job and able to finding this bug. However, and this is what you will see the other side, is that whenever no test is able to detect this mutant, that means that anybody who would make this mistake in production or in production code would also make it all the way through. So that's bad. Now, it's also important to note that the mutation analysis can be relatively expensive. We'll cover some optimization later, but if you think about the fact that we can generate thousands of mutants for relatively little amounts of code, we have a very big test suite that you'll be executing many tests many times to find possible mutants. In the end, what I also forgot to mention, so if a mutant survives, that might be an indication that you're either missing a test case, or what you often see is that you're missing assertions. That, for example, that setter that was removed, if you don't assert the field, then it will not be detected. So we now covered the theory a bit, so let's have a look at the tools. And mutation testing is not new. As I already mentioned, it's a tool that's been around for quite some while. The first tools for Java were created in the early 2000s. So these were from 2001, 2003, 2005, respectively. However, the problem with these tools was that they are mostly come from an academic background. People who are doing research on test effectiveness and seeing, for example, how they can generate effective tests. And what I noticed also during my thesis is that there's a different use case between industry and research. With research, it's fine that it takes a couple of days to set it up for a project. And it's fine that it takes a couple of days to run, because we mostly care about the results and we only need them once, and then we can continue with our analysis. Of course, it doesn't go for all, but you see this often, and it was also the result of these tools. They were really hard to use, very limited, not actively maintained. None of these go beyond Java 6, as far as I have found. However, this research did help us in the tool that eventually did make it to industry, which is PyTest. PyTest, or also called PIT, was created in 2011 by Henry Coles. And there are some nice things in here. Some of the previous tools also did this, but the first one is the bytecode mutation. As we said, we don't want to test the compiler, so we do mutations on bytecode level. That already makes things a lot faster because we don't have to compile. The other one is using code coverage to determine which tests we want to execute. So what PyTest does before it does the mutation analysis, it first runs all the tests, and for each individual test, measures if the code coverage is present. Yes, for each measures which code it covers. Then it knows for each piece of code which tests are related to it. So whenever you have a mutant in this piece of code, you know that you only need to execute these 5 tests because all the other ones are not going to reach this anyway, which makes it already, again, a lot faster. And the other thing is that it's really easy to use. Instead of having lots of different setup scripts, it's a Maven plugin or a Gradle plugin, and it's also actively maintained. Whereas the other one stopped at Java 6, this one is also supporting Java 21, all kinds, JUnit 4, JUnit 5, the different testing frameworks, which are really, really helpful. So this finally opened the door for us to start doing mutation testing. And just to show you how easy this is, it would be as easy as adding a plugin and you run the Maven code. And of course, I also want to show you this. So I want to do a quick demo. So we go to IntelliJ, and what I have here is a project. We call this is the proposal service. And what we have is some code that is effectively identical to the example you saw for the code coverage. We have a submit method. We check if the number of open proposals is not exceeded, and we check if the deadline hasn't passed. And then we return either failure or success. Now, for the sake of the demo, I also added a duplicate copy of this. So if I would diff them, you see that they are identical. Proposal service and proposal service 2 are the same. However, the test suites for these, we have a proposal service with also the free tests we saw from the slide. So we check success if there's no proposal deadline in the future. We return a failure if the number of open proposals has been exceeded. And we expect a failure if the deadline was yesterday. But there's now a difference with the proposal service 2 test, where we do exactly the same tests, but now without any assertions, just to give you an idea between a good test suite and a bad test suite. As I said, if you look at the POM file, I did a bit more here. I added a plugin for JUnit 5, and in this case, I don't want to run any tests on my models. And the other thing that I added was Jacoco for measuring code coverage, where I also excluded any models. Now, if I run this with the Maven goal, which doesn't take very long because it's a really smart project. So the bigger the project, the longer this is obviously going to take. And then you can see how many mutants were generated, what the code coverage was, and how many mutants we in the end didn't cover. And now I want to go have a look at the reports. And the first report that we have is the code coverage report from Jacoco. You might be familiar with this one. We have both services, and you see that they have the same amount of coverage, 100%. Having a look at the proposal of the mutation testing report, we can now see that there's a difference between the two services. And this is exactly the goal here. We want to be able to identify pieces of code that are actually tested, but turns out that they don't kill many mutants. So whenever you investigate a mutation testing report, the most interesting ones are the ones that have very high coverage and kill barely any mutants, because this is an indication that we have very poor test quality. However, let's have a look at how such a thing looks. So if your monitor is able to distinguish between the colors, it's a bit sometimes hard to spot, but you have light green for code covered, but no mutants. We have darker green for mutants that are killed and the code is covered, and we have red for code that is covered, but no mutants have been killed. Not all mutants have been killed. And what we can see here, if we look at this line, we can see that there's one mutant that survived, which is the one that changed the conditional boundary. And that's correct, because in our tests, we never tested the edge case of when we have exactly 3 open proposals, whether that is still acceptable or not. And what we also didn't test is whether our notification service was invoked, because we forgot about that. So you see also that the removed call to the notification service failed. It survived. And then at the end of the report, you can also again see an overview of the mutants which were killed and which were survived, and a set of mutators that were used, and the tests that were examined. Now this also looks nice. However, the reality is, as I said, for larger projects, it takes a long time. When I was doing this for my thesis, I had to analyze about 5 open source projects, and then you notice that without any optimizations, it can take days. And even though I could do this, I had to run it. I had to generate a lot of test suites. So for me, that was a bit suboptimal. Now, to help with this, the first thing that I always suggest when people want to start mutation testing is to start small. Start with a single package, a single test suite for that package, so that you know at least that it runs. So in this case, utility tests are often quite straightforward. And another thing is that good to keep in mind is that PyTest by default only runs on a single thread. And if you have more threads available, it's good to utilize this so that it can tremendously increase the speed. So once you sort of have the base set, you have it running, now you want to start expanding it to the rest of the project. That's where you should start with tweaking the performance. And there's many different ways we can do this. So I want to go over a couple of steps you can take to sort of find a nice sweet spot. And the first one is to reduce the number of tests you run. And there's some obvious candidates for this, but that also depends on your test setup. So in the past, we had acceptance tests or integration tests as unit tests. Especially with Spring Boot, you can do quite some tests that cover effectively half your code base. If you're testing your endpoint all the way to the database, that means that you have a relatively large slice of code covered, which also means that there's a relatively large slice of code for which this slow test is being run, because those acceptance tests, especially if they go all the way to the database, are often relatively slow. This is a trade-off. If you exclude them, that means that you will also not kill the mutants that are in those slices. But ideally, we would also have unit tests for this, so we should be fine there. The same for the database tests. Database tests are usually pretty straightforward, and there's not a lot of code to mutate in a repository. It's not always true, but if this is the case for you, you can also exclude both the tests and the classes so that you speed it up again. Or if you have just specifically very, very slow tests that cover, maybe do a small performance test, of course, it's not useful to use these. You want to exclude them from mutation testing. Now, we can reduce the number of tests, but we can also reduce the number of mutants by reducing the code that is being analyzed. And the most obvious one for this one is generated code. We don't test our generated code, so we also don't need to analyze our generated code. But there's more. What I found a particular funny example was PDF generation. If you have ever written a PDF generator or like invoice generator, then you know that it's filled with mathematical operations to calculate the offset, to see the font size, to make sure that everything is aligned in the right place. Is that a fairly big PDF generator can already generate 1,000 mutants, also because a lot of void statements are in there, depending on the library you use. Whereas 1,000 mutants, and usually there's a couple of tests that you only need where you do bytecode comparison of the generated PDF. So you already have quite strong tests there. And then it might not be useful to do 1,000 times PDF generation if you already know that this part is fairly trusted. Then there's the database tests again. If we're not generating tests for it, then we also don't have to generate code for it. We don't have to generate mutants for it. And the last one, the threading, things related to threads are always a pain to test because of threading issues. But they can also be it can also be a pain for PyTest, especially if it's multi-threading and you're already running it in parallel. So it might be good to keep them out. Yeah. And another nice feature about PyTest is that it's still experimental, but it supports incremental analysis. And this means that it stores the result from your last run, and then it starts to compare which changes you made. And based on that, decides for which mutants it will run a test, or which tests it will run for which mutants. For example, suppose you have a class with 10 mutants in it that is covered by, say, 5 tests. If you don't change the tests or the mutants, you don't really need to rerun this part and then save time with it. The nice thing is that this is also used as the basis for, I think, the pull request integration. So there's a pro version of PyTest called ArcMutate, in which they also added support for GitLab and GitHub, Bitbucket, and most version control systems, where it's in your merge request, in the diffs, sort of shows you which changes were done to mutation score, which is fairly powerful. It's also not that expensive, so if you have budget, that might also be interesting to try. I'll also come back to that one later. Another thing, which is not necessarily related to performance, but also to clean reports, is that one of the things that we often don't test is logging, which is most cases also fine. We don't need to test the logging. However, all these log statements are void statements, and sometimes also contain some math operators. So in this example that you see here at the bottom, this would be 2 mutants that we're never going to find because we don't test this. Now, by default, PyTest already exclude all invocations to logging libraries, but maybe you have some custom logging facades, then you also want to add this. Or maybe there's some code related to metrics, to some custom piece of code that you repeat all over the code base that you don't really test, then it might be useful to keep this out so that it's not mutated, keeping your reports clean. And again, less mutants also means a bit more speed. Now, another thing that we can tweak is the set of mutators used. So the default set of mutators, this is the set of mutators that are available. At least it was the last time I checked. It could have been that more. It's also nice to see that if you look at the PyTest in research and in papers, is that within papers, they are research papers, they are adding new sorts of mutators that are sometimes then being adopted by PyTest. By default, there's only a small set that's being used. This is sort of seen as the best set, where you have the most stable and hardest to detect mutants there. You can add more. So this is the default set. If you start adding more, that also means you generate significantly more mutants with a significantly more execution time and also more possible false positives or things that you might not deem relevant, whether you want to test whether your constants are correctly used, etc. Have a look at the PyTest documentation where they explain the different mutators. What's also good to mention, by the way, is that in the pro versions, I haven't used them yet, but we're going to try this out soon, is that they offer more support for example, Spring integration tests and some JUnit 5 optimizations, and a larger set of base mutators. Another thing that you can encounter are something called equivalent mutants. And what you see, so we have a while loop that increments I in each iteration, and at some point I reaches max, and then we break out of the loop. If we would replace equals to with larger than or equal to, it will still always break when I is equal to max. So it will never be able to spot this mutant because these are functionally equivalent. So if you, especially with the other mutators, which are not in the base set, there's a chance that these might happen. And it's good to keep in mind when you're inspecting these reports that you could come across some of these. Now, having decided you want to use mutation testing, it's also nice to know that it's easy to integrate with your CI tools, with just like you saw before, the Maven step, which also can be, the Maven call can be configured to break your build if your mutation score goes below a certain point. And there's also plugins available for Jenkins or Sonar. And then, of course, in the pro version, also for your different VGS tools. Having said that, and having explained sort of mutation testing now, it's also good to keep in mind, as I said before, it's not necessarily a silver bullet. It's computationally quite expensive. And going through these reports, especially for larger things, if you started cutting in your unit tests, it's quite time-consuming to sort of investigate whether these are indeed issues or not. So it's good to ask yourself a couple of questions. And I always start with the base set, which means that you should consider mutation testing. For example, will people die? Based on the mistakes you might create, will there be a lot of money lost and people die? Or in case of self-driving car, money and reputation and people. Then the quality requirements should be so high that you would do any possible thing you can to reduce the amount of bugs that might make it to production. So yes, you would want to use mutation testing. However, in practice, I have not worked on any of these projects, and so far my software has not been able to kill anybody, as far as I know, I hope. There's more relevant questions that we can ask. For example, are you using code coverage? Are you using code coverage as a stopping criteria to stop writing tests or to evaluate when your sprint definition of done, your goal was achieved? Or when you're reporting to management on you're adopting a project from another team and you want to know what the status is, then actually I think you should consider using mutation testing. Because as you see, code coverage is in the end, it's a nice indication, but it goes and falls with the quality of the tests themselves. Because if you have a very nice test suite with 0 assertions, then this number is very misleading. So then consider it. Another one is the cost of fixing a bug. For example, the first time I worked, we actually get back to the money example effectively. My first job, I was working for a customer, or I was working on a product, some enterprise software that only runs on-premise and only runs with customers that were mostly governments or very large enterprise projects, where the release window, especially with these government projects, we had a release window of, say, 2 weeks a year in which we could upgrade, which means that if a bug makes it there, we have a serious issue, and it costs a lot of effort and bureaucracy to get things fixed. Then yes, you want to do also, that's where we started using mutation testing as well, just to make sure that we really don't get bugs into production. On the other hand, you have these startup projects where I also worked on, where it was more a fix fast or fail fast, fix fast mentality, which means we were able to deploy to production within half an hour. So whenever something was detected, we didn't have a lot of customers yet. It was okay that the bug was there, but because we could also immediately find it quite quickly. We sort of used our customers as tests. It really depends on the mindset. If you want to move forward quickly, then you maybe not want to spend a lot of time in writing elaborate test sets. But that's a more generic question. So if you have a very high cost of fixing a bug, like we had in the first case, again, consider mutation testing. And the last one, because some people go to a conference, then they see something that they find very interesting, and then they start implementing it. And I always like the analogy with Sonar. It really depends on the teams, but I've seen plenty of teams where there was always one very enthusiastic person that really liked Sonar, and the rest of the team didn't really care about. And at some point, that person left. Now we have Sonar running, and nobody's looking at it anymore. We're wasting resources. The first thing you should do is take your team with you, convince them. And this actually goes in general. Whenever you, so when you get home after this presentation, or if you're already at home and you think, hey, mutation testing could be interesting, just run it once first locally and generate a single report. That single report gives you sort of a feel of what the current state is of your test code. If it turns out that you're working in a very high-performing team and everybody is already very keen on writing proper tests, then you'll see that the mutation testing report reflects that, and it might not even be that beneficial to edit because the team is already doing a great job, and adding this report and then looking at this report just would add overhead. However, if you then run this report, and I've also seen that with colleagues who were at certain customers, that it suddenly showed that there were quite some painful areas which had high coverage but very low mutation scores. And then upon further inspection, it turned out that there were quite some issues with, for example, outsourced developers that had different requirements quality, but also parts of projects where people were not spending the time and attention to tests that they should be giving. There, again, it was very interesting to sort of include mutation testing in the process just to force people to sort of up their game. You can use it to sort of educate the juniors that they should be writing proper tests. And then, then start using it. So come run it locally once, generate the report, talk to the team, show them the results. And if the results are indeed bad, take the team on this trip to mutation testing. Now, to summarize, code coverage is really about how much of the code is tested, whereas mutation testing is really about how properly did you test the code. And then when you start mutation testing, start small, start expanding, and then tweak for performance. And that's it. Already a bit faster than expected, but thank you for your time. And here's a bunch of useful tools. The things, by the way, that I mentioned are also, the tools are very widely available. So if you have Python, you can use Mutants. There's even for PHP, there's mutation testing frameworks. For the front end, I would recommend Striker from Info Support. If you have Kotlin, have a look at ArcMutate as well, as it can be quite useful. So now I think, are there any questions, or is there a way for me to go?
Actually, we have a bunch of questions, so be ready to answer them.
Okay.
And first of all, at the beginning, you mentioned about quality, so that was not afraid that you finished a bit fast. Anyway, this was pretty quality talk, and thank for all your insights and for sharing your knowledge and expertise. And of course, it was pretty useful to see some practical tips and tricks and some pros and cons, because you can see value on with a comparison and on real examples, right?
Yeah.
And that's why it was pretty cool to hear that. Thank you. And also, I want to mention that I would like to try it on my project, and we'll back to you soon.
Yes. Yeah. Please let me know in the chat as well if you think after this presentation, yes, now I want to try it, because that means that I achieved at least something, and otherwise, at least people have another tool in their kit.
Yeah, so I can mail your message. Yeah. So let's switch to questions. I'll start from the beginning. First question from Mike. Do you recommend to avoid mocks in testing because it might lead you to test for tests?
Yeah, mocking in tests is always an interesting discussion. If you want to do pure unit tests of every class, you can't really avoid writing a lot of Muon mocks. It really depends on what you want as a team. I'm not sure if it leads to testing the tests, but it does lead to test code that is very hard to maintain. You're not necessarily testing the tests more or less if you add more mocking code, but it does make a lot more painful to make changes or refactorings, because you're constantly checking if each call makes sense, and then maybe it's not always useful. I find it a bit hard to answer this question though, but
oh, it's quite good, thank you. And we have another one from the same person. How challenging is it to integrate mutation testing into existing build process?
So it shouldn't be very challenging. As I said, it could be as a matter of adding the Maven step to whatever goal you use for running, or as a separate step. Make it a parallel step that's non-blocking, where you run the mutation testing report depending on which tool you use for the pipelines. It should be fairly straightforward, but it's good to first test this locally and see if you're not stuck in infinite loops or have some weird example, especially with Spring and an integration test in Spring. It might not be super useful unless you go for where you could consider the paid version. So for example, with Spring, you have the context. So effectively what the Spring support from ArcMutate does is that it by default adds the dirtiest context at top of each test so that it doesn't cache anything and your context is constantly refreshed. That's to keep in mind, but that's what you can also do by testing it locally to see what works and what doesn't work for you. And then if you know that it works, you can start adding it to the pipeline, pushing the reports and artifact.
Cool, thank you. And we have another one, from Andrew. Can we combine the test-driven development approach and mutation tests?
Sorry, can you repeat that?
Can we combine TDD, test-driven development, and mutation testing?
I mean, yes, you can, but I'm not sure if it would improve the speed of your process. So with TDD, of course, you write the tests before you sort of do the implementation, and then incremental, you add a bit of implementation, add a bit of tests. Now, what you could do is need, after each implementation step, run mutation testing to see if you possibly missed some tests. But I would not do this at the same speed if you do pure TDD. So then I would rather do this at the end and then see which cases you possibly have missed. You could do it though, but then make sure you run mutation testing only limited to the very piece of code you're working on instead of waiting an hour every iteration. So you can limit, as you saw, the tests to a certain class or to a certain test or both. And then yes, you can consider it. Might be useful. It's an interesting approach indeed to see if you have any blind spots. So.
Yeah, experimenting also sometimes pretty good approach.
Yes, thank you for the question.
The next one. Okay, how can the results of mutation testing inform improvements in a unit testing strategy? I believe you covered it a bit in your presentation. Not?
Can you? Sorry, I can't read them right now because I have my own presentation open.
I can repeat. How can the results of mutation testing inform improvements in a unit testing strategy? It's actually about mutants, correct?
Yeah, that's exactly what mutation testing is about. Is to check if your tests, so your unit testing results or your test strategy, should improve, because you will see your blind spots better, and you see where you can improve. I think, again, the one that's hard to answer directly. I can also check it in the chat later, but
no, it's pretty good answer. Yeah. It's pretty. The next one also pretty similar to how to integrate into build process. Here we have a question: how can mutation testing be integrated into a continuous integration, continuous deployment pipeline? It's pretty similar to integrating a build process.
Exactly. You can add the Maven build, and like I said before, don't make this. So you have a commit build. I would not recommend to make mutation testing part of the commit build because it might still take half an hour.
Mm-hmm.
You don't want to block your builds for half an hour. So you can add some parallel steps or non-blocking steps, so that, for example, your build is at least pushed to whatever Docker repository you have, and then later on you still have the report. You can also do this, by the way, as a nightly if you don't want to be running this all the time.
Cool, thank you. We still have few
we have time.
Ready. Yeah. Next one. Pretty interesting. Can you share an example of how mutation testing helped uncover significant issue in the project you worked on?
So that's a good question. So in practice, I think I mostly have the story from a colleague where they had this where they didn't necessarily found more bugs in the production code, because usually the problem with a bad test suite is not necessarily that you have more bugs in the production code, because the production code is always also tested afterwards. You have users. The problem is more that you want to prevent new bugs from making it there by adding better tests. So what I do see also in my current job is that we have tests where their assertions were missing, which made me, for example, introduce new bugs because I added a new feature, I refactored some things, and then it turned out that I broke some existing functionality. Now that could have been prevented if I would have used mutation testing there, because then the mutation testing could have probably shown that we were missing assertions. So it's not necessarily that when we started using mutation testing, we found more bugs in the product, but we could prevent more bugs from making it into the product, mostly. And that's also what we saw especially at least in the current project I'm in, where we sometimes see that there's some space for improvement, which is also why we want to start trialing ArcMutate. But also the example with outsourcing, where there was a whole part of the front end that was not properly tested, which means that there was a high probability that when you did a large refactoring, that you could introduce more bugs, which means you lose confidence in your test suite, which is a really bad thing.
Got your point. Thank you. I can say that we have stream of questions right now.
Well, that's the nice thing about finishing.
I'm really interested in that title, title of that. I know your presentation. That's why I initially say that it's not that commonly discussed and commonly used technique. That's why it's pretty interesting to discuss. So the next question. Oh, actually, it's connected. Why is they not that popular? What are your thoughts on that?
Well, so a big part is people don't know about it. Now the question is, why do people not know about it? Probably because it's sort of a chicken egg thing. Yeah, so one of the reasons is still that it in practice, what you see, so mutation testing, for example, extremely powerful if you're building libraries, especially closed libraries, where you do mathematical operation or a lot of business logic. But if you look at our more default application that we write, where it's a lot of JSON in, JSON out, and some minor processing, you see that there's a lot of overhead that we don't usually care about testing, so then mutation testing might also be less interesting. And another reason is that I think it takes time to go over the report. Other than that, I don't really know why people are not using it. I think that it's a blind spot mostly. I think that more people should be using it, especially since a lot of people do use code coverage. But to get back to what I said before, you don't necessarily need this in your CI/CD. Just doing this once every year, or once every month, or once every week, just to get a sort of a feel of what the code base is. That's already very useful. I haven't seen a lot of people that tried mutation testing and came to the conclusion that they didn't like it. It's more that a lot of people just didn't try it.
Oh, cool. I hope that like people that watching right now this stream will definitely try it right after today's. Okay, today is Friday, maybe from Monday. Yeah, Monday project.
If you're enthusiastic, then but yeah. Maybe wait till Monday. Enjoy the weekend. Or of course go to the conference tomorrow, right?
Yeah, the offline part. You can still come, maybe. Yeah. Why not? You have a whole night for that. And 3 more questions. I don't know. Two pretty interesting. How to avoid infinite loops with mutation testing?
Yes, it's one that I actually didn't cover. But the one thing that PyTest also does is when it initially measures the code coverage of each test, it also tests the execution time of each individual test. And then when it sees this is configurable, for example, when a test takes 1.5 or twice the amount of time to execute against what it was before, so probably the mutation then created somehow an infinite loop, which is possible. And then it says, okay, we deem this as a kill because if you would have done this yourself, then also this test would have been running infinitely. So we see this as a mutant that's dead, but it's detected, and the PyTest will not run indefinitely. So you don't have to worry about this. That's pretty neatly done, and you can configure whether it's 1.5 times, 2 times, 3 times, which you need. But a good question.
Oh, great that is included. And one more configuration question. Can we customize the number of generated mutants and mutant types?
You can customize the set of mutators. So we have, you can see it on the website as well. There's a large set of mutators. There's a base set that's selected by default, but you can just configure the Maven plugin to use a different set of mutators. Maybe you don't like one, or you really like another one. You cannot really limit it in an absolute number, like stop at 1,000 mutants as far as I know, but you can have less mutators or just have less code to mutate. Another one that you might usually not mutate is all your setters and getters, for example. That's also, the models might not be interesting.
Thanks a lot for your answers. You covered pretty big bunch of questions. Thank you. Yeah, that you have a time to answer all these questions. Yeah, appreciate that, your time, and that you prepared such a great presentation. And actually, that's also kind of support to your support of a conference. You support Ukraine. Thank you for that as well, that you participate in that event. And also looking forward for the next events where you can participate, and especially on site, in person.
Yeah.
Looking forward for that. Yeah.
Me too. Thank you for all the hard work and organizing this nice conference and having me. And have a nice evening, I guess, for everybody.
Yeah, you too. Have a nice evening.